So the K has geometric origin. So let me recall the notation. So X is some smooth scheme over my base field K, and we have a smooth divisor, and so this is K is the local field at the J point of this smooth divisor. So it says the following this. So so we are interested in this Galois covering, but we can assume that it comes from this diagram. So why is so this is the finite covering of smooth varieties, and so this U is the complement of this smooth divisor, and so here we have Galois finite eta Galois covering of the same group G. So this is Galois covering, and this is the same Galois covering of the same Galois group, and this is also the complement of smooth divisor like this. Okay, so this is the setting for us. So now we start with geometric construction. Okay. So first I define a log product. So and I like this P. So how we define this? So we start from this log product. So yes, yesterday I introduced such a log product. So here we have a smooth scheme and we have a smooth divisor. So we can define such log product. So this is above usual product. So we blow up at D cross D and remove some proper transform. Okay. Then we can take a second projection. So this is just the completion of the second projection. Then we have canonical. So here S is the spec of OK. Sorry. So we have a canonical map from this S to X because yeah. So this is just OK. So we have a canonical map from S to this X. Okay. And we can define this just by fiber as a fiber product. So I will give some concrete example in a minute. So this will be our P. Okay, and if we and we have open subscheme here, and we can and the base thing. This doesn't change anything on U. So if you take the base change by this open margin of this diagram, then what we get is the following. So on the base we have U, and because we remove something above U, we only have U. So and on the J, on the J, the base on the inverse image of U, we only have the spec of K. And this is defined by Cartesian diagram. So we have on the J fiber we have just K. So this means that so this is the spec of OK, and we have J point, and on the J fiber, the J fiber of P is just the base change of UK. And so UK is just U cross K spec K. So we have a smooth variety of little K, and we have this UK is just the scalar extension of my to the local field. Okay, so this is maybe the base scheme. So I just copy the what's going on here. Okay. And we have canonical section here. So this has a section here because so we have the diagonal map here, and we lifted it to logarithmic diagonal. So this gives a section here, and this induces section there. So this is so this is also induced. So this is induced by the logarithmic diagonal. Now, okay, so now we plug in this covering. So at the base change, we have covering here, and we can take the normalization. So this will be the normalization. So so we again have a Cartesian diagram. And let me remind you that this is spec of okay. And we have finite covering spec of L. So this is L is the this finite Galois extension we start with. And because this is normalization, we have a canonical map here. So this should be regarded as scheme theoretic version of the map. This is the geometric version we have seen yesterday. So yesterday, yeah, we had seen we have seen a map of digital analytic disks, and such that the inverse image of the origin is identified with the Galois group. So this diagram is a scheme theoretic version of this one, or this one. So yesterday I forgot to say why this inverse image is identified with the Galois group. So let me explain now. Okay. So the disk up is identified with this set. the set of OK algebra homomorphisms from this polynomial algebra to OK bar. Because so these xi are in K bar, and the condition that the variation is at least 0 says that there are the element in the integer ring. So, and if you pick n elements of integer ring, they define algebra homomorphism from polynomial algebra. So we can interpret this as a set of homomorphisms of OK algebra. And now, the inverse image of 0, yeah, here. So the map here is defined by sending this point to that point. So you just substitute into these polynomials. So, and the condition here says that so this homomorphism kills these polynomials. So in this way, you see that the inverse image of 0 is identified with the set of this homomorphism. But this is nothing but the presentation of OL or integer ring. So this is where we started with yesterday. And yeah, now we see that so this is a set of homomorphism of OK algebras from OL to OK bar, and we can identify it with the Gaga group. Okay. So now we have obtained schematic interpretation of the diagram we have seen yesterday. And yesterday, after having such diagram, what we did yesterday was to shrink the radius. So now we have to make algebraic construction, algebraic construction corresponding to shrinking the radius. So yesterday, after defining such diagram, we made a construction like this to define upper numbering filtration. So there, so we started with the map here from a disk to another disk, and what we did is that we took a smaller disk and we look at the inverse way. So we want to do so this is a picture in this geometry, but we want to do it algebraically. Okay, so how we shrink the radius? So yesterday I said that shrinking the algebraic operation corresponding to shrinking the radius is blow up. So I have to do some blow up. Okay, now I take a rational number. So yeah, so this corresponds to uh, to the radius of this disk. Okay, and I need to take some finite extension. So this is the finite separable extension. Yeah, because uh, so you may regard this as a rigid variety over K bar, but instead of going to separable closure, we can take some finite separable extension and we can replace it by a larger extension. Okay, so and let E denote the ramification index. So first thing I need this such extension to make the to kill the denominator of this rational number. So I assume that this product is this is integer. So so first we use the the denominator. Okay. So and let S prime be the spec of the integer ring, and the PS prime will be just the base range. So P is the log product here. So this is X star S. Yeah. Okay. So now we are ready to make blow up. So I'm going to define PR of S prime. So this is blow up of. So first we make blow up of PS prime at, so I need more space at so spec of OK prime and divided by the power of this mass area and to e to r sorry yes so to e to r so this this is already made integer. So this, so we can, so this is a subscheme of S prime. And this is, we can embed this into PS prime. So, yeah, uh, maybe one. Yeah, yeah. I said that uh, we have a canonical section of P over S induced by log diagonal. So yeah, it was already there. So this section induces that section. So this is induced by log diagonal. So yeah, so we can regard this small cross subscheme inside this uh, this base change. So we can blow up this point and then remove that proper transform of the closed fiber. So I will draw a picture for you. So we start from P over S. So this is some smooth scheme, and we have closed point and closed fiber. Now I take base change. Sorry, I and this has canonical section induced by. So this is section. So induced by this log diagonal. And we take base change. So this is PS prime. And we have, so this section, this is section here. So S prime is embedded in this PS prime here. So yeah, so this guy is this guy. And now we have infinitesimal thing here. So we blow up this point. Then we get to something like this. And this is proper transform. And this is the exceptional divisor. And we have map to S prime. And we remove this guy. And the rest is the PS prime. So this is a construction. So let me give you a concrete example. So X is just a affine space as before. Okay. And D is defined by T1 equals 0. Then our local field is just so we have parameters from the remaining parameters and uniformizer is this T1. Okay. Now I take product. So this is just spec of okay. And yeah, I need to change. I need another parameters. So yeah, so this is just base change. So but I need another letters. Defined letters. So let me call it S something. Now P P is so this is base changeable log product, and so this P is spec of OK U1 plus minus 1, and remain the same. And this U1 is S1, so we have relation like S1 is U1 times T1. Or in other words, U1 is S1 over T1. So now, I'm so so this is the first block, and to study higher ramification, we need to make another the second block. Okay, so now I describe. So I make this base change. So to have base change, you just put the prime here. So PS prime is spec of OK prime. U1 plus minus 1, S2, and so on. Now I make the second blow up. So this guy is spec of OK prime. Oh, yeah. Mm, yeah. V1 to VD. Well, in other words, so let me call this algebra A. This is spec of A, but we so blow up means that we introduce some fractions. So first one is u. So you subtract one and divide by this phi prime e to r. So this phi prime is a uniformizer of OK prime. And yeah, you is yeah. Maybe it's better to say that. So here, this section is defined by equation like u1 equal 1, and si equal to ti for I to from 2 through d. Yeah. So yeah. So the idea here is yeah, the idea here is denoted by u1 minus 1 si minus ti I equal 1 to d, and phi prime er. So this point is defined by this ideal in our case. So we introduce fractions. This guy divided by this guy. So I continue like this. T2 pi prime er, and so on. Is d minus td divided by pi prime er. And by putting them like this, so sorry. Yeah, yeah, we check that this algebra is isomorphic to this polynomial algebra. So this is the construction corresponding to shrinking the radius. Okay. So now we look at the covering. So we have defined this scheme. But this construction, so so I made this construction, but this doesn't change anything on the JF fiber. So 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 this still has that yeah the JF fiber is the same as before, and we have covering here. Then we can take the normalization as before. So this is the normalization. Okay, but uh, but so so we have seen that this is a nice scheme. So this is in this case this is just polynomial algebra. So this is a affine space. But in general, it's not necessarily a affine space, but this is always smooth, always. But this can be not so good. So, but we can make it better by choosing by make, by making this k prime bigger. So so that so we can take k prime so that uh, the following condition be satisfied. So the first condition that so we have already seen this first condition. This product is integer. And the second condition is that so we can take k prime arbitrarily larger. So we can assume that our Galois extension is already contained in k prime. And the last condition, so this is a non-trivial condition, but so this is a consequence of Web's theorem. Uh, but anyway, so I will not explain what this means, but in any case, we can assume this condition. The condition is that this guy this QS this normalization has uh, uh, a geometrically reduced closed fiber. Reduced closed fiber. So what does this mean? So F bar be this is algebraic closure of our the residue field. Okay, okay. So so we are working with this finite extension, and yeah, the residue field of this is finite extension of this f. So we can we have a natural map like F bar is also the algebraic closure of the residue field of this DVR. And and this this condition is that the Q let me denote QF bar R. So this is the base change. Sorry, QS prime R times spec of OK prime spec F bar. So this is the geometric fiber. And the condition is that this is reduced. So, um, So this theorem tells us that if we if we take this K prime sufficiently large, then this geometric fiber will be reduced. So we can find such sufficiently large finite extension. Okay. So now we are ready to define we are ready to define the upper number filtration. So, so let me copy the diagram up. So UK prime, VK prime, PS prime R, QS prime R. Okay. And here I have uh, canonical section induced by log diagram. And and we started with yeah. So we started with this diagram. So yeah, so we have this diagram. So on the Drake fiber, we have the base change of this. So the base change of this is spec L tensor K prime. So we have this Cartesian diagram. Yeah. So this is the Drake fiber. And by our assumption that this splits, yeah. So by this condition, we can identify this with G. So we have not reduction map from this finite set to the closed fiber of yeah, QF bar over. So I use this map to define the upper number filtration. So the log is consists of element in G such that image of sigma uh, in this scheme lies in the same connected component as the image of the identity. So this is uh, the algebraic definition of the algebraic interpretation of the upper number filtration. So in the rigid picture, um, so we have yesterday we have seen this picture. So in this rigid geometric picture, we pick up the point, the element in Galois group, which is contained in the same connected component, And here we also use connected component. So this is the corresponding notion. And so this picture is interpreted algebraically this way. Okay, so let me give you a concrete example here. So K will be as before, and we study Artin-Stein equation, Artin-Stein extension. So uh, the the character of the absolute Galois group into uh, cycle group of order P. So P is the characteristic of K. So we are in the equal characteristic situation. So this is nothing but H1 of Galois cohomology. And we know that this is identified with the quotient of additive group by this subgroup by Artin-Stein theory. Now, uh, so this additive group is has canonical filtration. So we can induce filtration uh, by from that filtration there. So the filtration. So this is the image of uh, power, negative power of sorry, negative power of the maximal idea. And so this is the dual of. So we have defined the upper number filtration there, and this filtration is the dual of the filtration we just defined. Or more concretely, so let A be a uh, element in this filtration such that the corresponding character. So let me denote the corresponding character chi of A. Chi of A is not in. So of course this is in field n, but I assume that this is not in field n minus one. Then and let so A will be finite cyclic extension border degree P defined by this Artin-Stein equation. And the Galois group is isomorphic to Z mod PZ. And yeah, for this group, so we have defined the upper number infiltration, and the result is that this filtration, yeah. So this is a subgroup of this cyclic group of order P. So this is everything or zero, and this is zero if and only if R is strictly bigger than this n. Yeah, n here. Yeah, so we can. Yeah, so I will tell you how we see this tomorrow. Okay, so this is the first example. Okay, So now, yeah, so so on this equation, we will be interested in the graded piece. Graded piece. Or or equivalently the last piece of the filtration. Or last piece of the filtration. So we go back to the general case. So for arbitrary Galois extension. And there is the last jump of this filtration. So 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 we have defined such filtration, and there is a uh, last jump. So last jump means that if uh, that this filtration is trivial if and only if if S is get so strictly larger than R, then the filtration will be trivial. So we have such last jump. So R will be called the last jump. Yeah, in this example, so this will be the last jump. This here by this assumption, n can be anything. Mm. Yeah. Mm. So I don't put any assumption on the residual field, so n can be divisible by p. Yeah, and so for this last jump, we know that this the r log is abelian and killed by p. Mm. But I don't go to the definition of the proof of this, but I will say something on the structure of uh, on the character group of this elementary P group tomorrow. So, so this is elementary P groups. So to know this group is equivalent to know the character of this group. So we want to determine this dual group. And so this is controlled by the so-called refined Swan character or refined Swan conductor. So there is canonical injection. So this is a canonical injection. Into some vector space. Maybe I need more space. So home F bar mk bar r mk bar r plus. So I will say what is this notation means to omega 1 x log d. So I take stoke sorry to Guzai tensor OX Guzai F bar. Okay. So this is some certain F bar vector space. So we have some canonical injection from this character group to this vector space. So here, so K bar is the separable closure. Of K. our local field, and mk bar r is uh, consists of element in k bar such that the normalized variation of A is at most at least R. So VK is normalized by the condition that the uniformizer has variation 1. So this is the uniformizer of K. And MK bar R plus, and we replace this inequality by strict inequality. So this is F bar space of dimension 1. And our geometric assumption, our uh, our OK is a completion with this local ring. So we have uh, so the map here is the completion of the this inclusion and the reduction. The map here is this map, and so this is locally constant sheaf. Sorry, locally free sheaf on X. Locally free OX module. So we take stock, and so this is I have a vector space of finite dimension. And yeah, tomorrow I will say some. So we yes yes so we, in the lecture by Bar and Weavers, we have seen some differential form, and here we also have some differential form. So if you study some ramifications, then we naturally find some differential form. And tomorrow I will explain how we get differential form out of ramification group. Yeah. Maybe. Ah, okay, so let me finish brief what I want to do tomorrow. So tomorrow, so we start. So yeah, so this is the end of the second part. Yeah, and tomorrow we going to the last part, and in the last part I will explain. So we already have seen some blow up, but blow up in geometric situation. So in global situation, global geometric situation. And then then in such global situation, we use some group structure, group scheme structure, and which explains this appearance of differential form. So yeah, tomorrow I will. So this is what I'm going to tell you tomorrow. Okay, thank you.